Hello, everybody. I trust that you can hear me out there. I want to. Kasia, can you hear me? Okay.
Yes, all okay. Everything. Thank you.
Everything is okay. Fantastic. And you can see my charming face and everything, and that's and you can see the presentation screen. Yeah.
Yes, indeed.
Excellent, excellent. In which case, we shall begin. What I'm going to do is I'm going to stop the video so you're not distracted by that, if that's okay with everybody. And then we'll just turn it back on again at the end if we come to some questions. But in the meantime, I'm going to turn that off and hopefully everybody can see the presentation. So for today's mini webinar, we're going to discuss voice evacuation in high-rise premises, and I'm going to run through some of the principles and objectives of that. So, if we're all ready to begin, I shall commence now. So what we're going to go through over the next 20 odd minutes is VA systems in multi-storey buildings, defining what the major risks are and the requirements. We're going to have a little talk about phased evacuation. I imagine some people are already familiar with the concept, but others may not be. So I'd like to talk about that. How the different system architectures that we use can make high-rise or multi-storey buildings safe in voice evacuation, and just look at a couple of the technical solutions that Ambient System has to deal with the multi-storey conundrum. So a little slide from our introduction to voice alarm seminar that we did a couple of weeks ago. What's the value of using voice alarm in any project at all? It just comes down to this idea that fundamentally people don't react very well to sounders. They react much better if they're given a clearly spoken and understood voice message. So you're looking at this thing, 13% of people react to sounders, and we all understand why that is. You know, if you hear a sounder going off, you don't really know if that's actually something to do with you or it's a completely different alarm. Could be burglar alarm, could be fire, could be many different things, but it doesn't give you any real information as to what to do. So the purpose of the voice alarm message is that the voice alarm gives you a clear, unambiguous instruction as to what to do, and therefore people are much more likely to go with that because they, you know, clearly link into what is happening around them very quickly. And you know, this is more important with high-rise than it is with other buildings where you can easily see the way outside. The building, you're on the same level as it, you can see a door, it's nice and straightforward. But in a high rise, obviously it could be some considerable distance from wherever you are to the outside world, to the muster point, if you have muster points in your car park or in the street outside your building. So in many countries, there's mandatory requirement for voice alarm above a certain number of levels of building. It could be between 4 levels, 6 levels. I've seen 10 levels in different countries. And you know, we define a voice alarm system as being in accordance with the EN54 standard. So I use EN54 standard equipment, and there will be a local standard which tells you how you should have installed that, and that varies very much from country to country. So here in the UK, it would be BS 5839 Part 8. In Germany, I think it's VDE 0828, and then there's one in France and civil defence in Dubai or wherever. And And those local standards will talk to you about the cabling type you want to use, the number of hours backup, that sort of information. And so we're not going to talk about those standards today. We're just going to talk about the solutions. So the standards we kind of addressed last week in the or the last webinar in the discussion about introduction to voice alarm. And of course, the voice alarm does give us some extra facilities as well. Not only are you able to use it during a fire scenario, but you can use them very much also for other security threats. And you know, that's been a big driver for voice alarm systems over the years, where particularly in a multi-storey type building, perhaps like an all glass office building, where you know, for whatever reason, you may believe that there might be an explosive device somewhere outside. You might not want to ask everybody to go outside where that device may be. You might ask them to move away from glass windows into, say, a concrete staircase at the centre, the core of the building, for safety there. So again, when we're looking at the risks to people in these buildings, it's not just about fire, and the voice alarm gives us the capacity to respond to things in addition to fire. So that's what we're talking about. The voice alarm, in essence, is connected to fire detection systems, but does give us the ability to respond to other scenarios as well. And you know, the big thing about these multi-storey high-rise type buildings is the limited capacity of the escape routes. So when you have a building which is 20 or 30 stories high, you may have one staircase. Hopefully you have a minimum of 2 staircases, and it's not going to work out if everybody goes to those staircases at one single time. That could actually cause you know, more damage and or loss of life than actually staying put if people crowd onto a staircase and then there's some form of crushing incident and so on. So we need to be able to efficiently manage the crowd of occupants, bearing in mind the limited capacity of the escape routes, to avoid confusion and therefore panic. And in the UK, this is a standard BS 7974 part 6, which defines how we look at the times, the various times that are involved in evacuating people from the building. What we see here is a typical set of periods from the time between when a fire starts and it's detected, and then you go into an alarm time, and then people start to think about moving while they work out, you know, is this really for me? Am I taking my bag? You know, do I need to turn off my computer before I leave my desk, and other such things that people think about. And then what we have towards the right-hand side of the screen there is the travel time. And therefore, what we're left with at the end is a margin of safety between the total available safe escape time, the asset at the top, and the required, you know, and what we're actually giving people, what we're actually getting them, what time it's going to take us to get them out in. And the thing with the high rise is that the travel time, we see the travel time in, or, you know, to the right hand side of the picture there, can be very long. So in this diagram is skewed towards the idea there's a small amount of detection time, a small amount of alarm time, some response time and travel time. And in our situation in high rise, what we know is that that travel time could be very long. I mean, I personally have been evacuated from a high rise building about 25 stories up. And it takes some time to get down the bottom when you're being part of an overall evacuation. So what's really important is that we minimize these other times, the pre-movement time, recognition and response times that make up that, so as to maximize the window for travel time, therefore retaining our margin of safety. So that's what we're really talking about. That's the value of the voice alarm, to increase the safe window for travel time by making sure that the pre-movement time is minimized. So let's look at how we are going to think about some of these things. So the first thing we're going to discuss, which we'll discuss in some detail, is how we do a phased evacuation, where we ask people to leave in sections, and how then a solution using distributed architecture, scalable, are going to benefit us, and also a little bit about the reliability and efficient power consumption, which is, you know, for maintenance, life safety, and also for the investors' purposes in ensuring that their building is reasonably priced to run in these times of high energy prices. So let's have a little bit of a look at what is phased evacuation. Phased evacuation is essentially where we are going to ask people to join stairwells at a different time. So we're avoiding the idea of a large volume of people coming onto the stairwell at once. And we're going to use a number of different messages, normally an evacuate message and a coded or not coded, remain where you are but be prepared to leave message, in order to give people the information they need to get them out safe in an orderly fashion. And then, so here we are again playing on our recognition and response time and passage time. And the diagram on the right-hand side, which looks like a big ladder of red and some times, is an example of a timing scenario from the Warsaw unit, which is a multi-storey building in Warsaw where we recently did some work. And as you can see, it's around 25 floors high, plus some basement. What happens is that we'll start with the first vertical column, if you wish. So if there is a fire detected on floor number 14, what will happen when that fire is detected is that floor number 14 will go into evacuation, as will floors 1, 0, and -1 to -3, because we want those areas to be cleared as people progress down the building. And then after 60 seconds, the evacuation will move both up to level number 15 and down to level number 13. So after 60 seconds, we then have floors number 15, 14, and 13 in evacuation. And then as time goes on, the next, after another 120 seconds, so it's 180 seconds after evacuation, level 12 will also join the evacuate ladder. Equally, if we move towards the middle of the table somewhere, so if we look at the situation that floor 21 has a fire detected on it, we will begin evacuating levels 21 and 9 at the same time. And the reason we're evacuating those two floors at once is that we have then enough time for everybody to be safely evacuated, for the stairwells to be used at maximum capacity by evacuating 2 floors at once simultaneously. In fact, I think 4 floors at once is the maximum capacity because of new instruction, because we could have then 23, 21, 11 and 9 all running at once. So you get the picture. What's happening is each 2 minutes or so, we're starting a new evacuation on a new level. And as we showed on the previous slide, we've evacuated the ground floor at the same time because those people can leave safely without really occupying the stairs. And we'd like to get them out the way, because then when our fire truck arrives with our fire commander, he can get in the building easily without having to fight his way past everybody leaving from the ground floor. So we've evacuated those people as a priority. That gives the fire detection, the fire brigade time and space to work on the ground floor. And then the other floors we're evacuating, like we said. And around the evacuation, we're also sending alert messages. So the alert message for every floor where there's evacuation, floor 4 in this case, floors 3 and floor 5, we're sending a separate message saying that there is a hazard, you need to wait where you are, further instructions will tell you if you need to evacuate. Obviously, if the fire turns out to be a false alarm, and we can resolve that without evacuating those, when we turn the fire alarm, reset the fire detection system and cancel all the calls, the people on floors 3 and 5 in this case should have, maybe packed their bag and turned off their PC, but should be sitting waiting for that further instruction, and then they would be able to unpack and get back to work. So that's okay. Where's that gone? There it is. So here we have this lovely little graphic here, which I'm just going to let run because our graphic designer Michael did it for us at great personal expense the other day. So again, you can see what's happening here. More and more areas go into evacuation. Other areas are going into warning. The ground floor has gone and basements have gone in straight away. And eventually we reach a stage where the entire building is receiving the evacuate message. So that really is the principle of phased evacuation. And that's what's going to help us get everybody out safely in time. In Ambient, we have effectively 3 sizes of system which we deploy in a high-rise project. We have the mini VES, which is a small 1 to 4 zone system, 640 watts. We have the mid-size systems, which are 8 to 16 zones up to 3,000 watts. And then we have the multi-VES, which is an unlimited scalable system. And the benefit of our approach is that we use the same networking and instruction sets across all the different products. So therefore, we can have one network, and that network can have these different types of devices on it, and they can all be readily controlled and interrogated from one laptop or from one HMI for control, or if you're using fire detection system interfaced at one point, that interface and cause and effect information can spread throughout the network regardless of which type of device you have. So we'll come back to the benefit of that in a second, but it's very much about this system scalability idea, because multi-storey buildings are not, it's not always clear what the purpose or how the multi-storey building will develop. From the time that an investor gets the permission to put up a building, they might already have one customer in mind. So there might be one company that has already decided to buy that building, have that building built for them, and they're going to occupy the whole thing. It's very often that the investor will create the building of, say, 30 stories, and during that time, they will then lease out the different floors. And as they lease those floors out, they might have some customers that just take 1 floor. They might have one customer that takes 10 floors. And also, they don't really know until they know what customer it is, the degree of cellularization on each level. So it might be that you want one big open floor, or it might be that, so I'll give the example of, say, a banking floor. So a banking floor would be one complete open floor where everyone is in conversation with each other, and speed of communication is very important to them. And at the other end, you could have a solicitor's type office where when you put all the solicitors in, each solicitor has their own working space. So you may end up with 100 or more small cellular offices on the floor. And this really then changes the way we're going to be able to have to fit out the voice alarm system in terms of the floors. So going back to our guidelines, if we were to have an open area, we might follow the guideline of having one ceiling speaker for every 36 square meters. So that's a 6-meter grid for placement, which gives you a good balance of intelligibility and sound pressure level mix across the whole floor. And when we look at that, you can see the difference in terms of how that might look in terms of loudspeakers on the floor. On the left-hand side, we have the empty office with 70-odd speakers on it, and on the right-hand side, we've cellularized up the office, and because we've then cellularized it, we need to put more speakers on, and without really then knowing how to do that, the ambient solution enables us to pick the smaller devices that we showed a couple of lines back, the mini VES and the MIDI VES, and potentially distribute them around the system. Distribute them around the building to give you the best combination of coverage and performance and cost. And one of the features of this is to be able to share amplifiers across a couple of different zones. So rather than thinking in terms of, oh, I've got one zone, I've got one amplifier per zone, I can say, oh, I've got 500 watt amplifier, and I'm going to run that with evac message or with coded message, and then I can link on whatever floors I want to that amplifier as I need them to be linked on. And so the architecture begins to look more sensible in a distributed fashion. So the distributed fashion enables us to use the fiber optic connection from one node to another. And then, so when we are having copper cabling, then we can still use smaller wire gauge, which of course is cheaper and easier to install, and is basically less wasteful. So distributing the architecture can make a lot of sense. And when we start to look at that, it can look like this. So this, for example, could be a project with 2 MIDI VES in. So on this area, on this diagram here, the bottom one could be a MIDI VES, it could be a multi-VES. We've got one zone which is running the staircase, and we've got other zones which are the general restaurant lobby lines for the ground floor, for the mainly public areas. And then we've got another rack further up the building which is doing landlords and tenants, loudspeaker zones, but now distributed further up the building. So this could be, four levels further up or 8 levels higher up, depending on the number of zones you're requiring per level and the loads. And so in this case, we've got the fire alarm panel at the base here. And so all of the fire alarm contact information is coming through PAVA rack A with fireman's microphone, which sits in our case on the fiber optic ring and is therefore linked to both the PAVA racks, and a couple of paging microphones for general purpose connected again into PAVA rack A. And one sort of simple enhancement to this is you could say, well, okay, that's great, but what happens if we lose the link between PAVA rack A and PAVA rack B? And that's actually nice and simple to deal with, because we have the ability to add a fire alarm panel into PAVA rack B, so we can have a direct connection between those two. And then in the event that there's a loss of communication between A and B, then the fire alarm will still be driving PAVA rack B. If it's got its local detectors there, those detectors have detected a fire, they will signal our rack to evacuate those areas. So it gives us a nice redundant set of connections, a little bit more security in terms of ensuring that our interface to fire detection is fully in place. So this is one for our investors. So in this case, our investor, he doesn't know yet quite how he's going to rent his building out. But what he's pretty certain of is that he's going to rent it out, and he just really wants to have his common areas on each level, which would be his toilets and the immediate lift lobby, and he will just really pay for those to be equipped. So it saves him money in the first instance. And he sets out a system a little bit like this. So he's made no effort to cover the general floors at this stage. And what he's going to do is that when he rents each level out, he will then ensure that the tenancy agreement will require the tenant to add their own voice alarm on each level. So in that case, we end up with this slightly more advanced system. So again, at the bottom, we can see the investor has paid for the staircase zones, the PAVA rack at the bottom, and the general areas up throughout the building. And then he has made the tenant then purchase the remote PAVA amplifier or rack and batteries directly interfaced with the fire alarm on each level. And then they've had to pay for their own loudspeakers and cabling in their tenant's area. And we repeat that floor by floor. One of the advantages this gives them is that they could then add a microphone on that floor if they wanted to make their own paging announcements in their own domain, or if they wanted to, for example, play a bit of music or use some of it as global conferencing type system. Other activities that they may want to use those speakers for are all up to them, and they can be safe that their system is entirely within their domain, and won't, their private company information won't sneak out into the rest of the common areas. But again, in the event of there being an evacuation, say for example, we mentioned before about a terrorist threat or something, then you can see that the fireman's microphone at the bottom is still connected to everything through the fibre optic ring, and therefore they're able to make priority announcements to all the people in the building, whether they're landlord, tenant, whoever they need to be. So, this is actually a pretty common model for bigger high-rise office type projects, and works well for most people. I think works okay for us as the installers, because we get kind of us as the manufacturers, because we sell a reasonable amount of equipment, because each level has its own or each tenant has their own extra system. It works well for installers because again there's a little bit more work to do, but it keeps investors' costs down and it gives the tenant what they want. So this is actually really the kind of nice solution for these projects. When we think about how we are going to make sure that we have a safe system for such projects, we want to make sure that we're not just skimming along the minimum safety level. We're really trying to make sure we've done the best we can. So in Ambient, we like to offer 72-hour battery backup power supplies. So that means that if a system has been left disconnected from the mains over the weekend while the building's basically unoccupied, should there be a fire on the Monday morning, there would still be enough battery to evacuate the building safely for an hour. We have a dynamic backup allocation feature, which I shall explain momentarily. And that effectively gives us the opportunity to increase our standby to operational amplifier ratio. So what are we talking about with this backup amplifier idea? On the backup amplifiers, you know, traditionally you can have one amplifier per 10, one spare per 10, or whatever, one per rack, or whatever you want to do. What we offer is slightly different in that our standby amplifiers are not allocated to a single failed amplifier. So what you often see is a sort of relay switched concept where once one amplifier has failed, the spare amplifier is then connected to take over the role of that amplifier, and it then remains allocated to that failed amplifier until such time as an engineer attends and resets the system. However, in the ambient solution, the standby amplifier effectively remains in float mode and is then connected to replace the failed amplifier as needed on a message by message basis. So it's only used during a paging event, and then after that paging event, it is returned to the resource pool. And therefore, one backup amplifier can cover for more than one faulty device. We also make our systems nice and efficient because, you know, that's again, it's good value for the investor. It's good for everybody not to waste electricity unnecessarily. And you know, we aim for 85% efficiency on our modern amplifiers, which I think is, you know, pretty much class leading type efficiency levels. These are some of the projects that we've done in recent times. This is just a domestic selection from Poland. As you can see, they all fit the typical profile that we've just discussed, being mid to high rise buildings, mainly office fit out. The highest being the Voce tower on the right hand side there, which is presently the tallest system in the EU, standing, I believe, at 304 meters. So it's nice to know that we actually have the experience of doing these projects, to know that the assumptions I've just been through with you are mainly correct. So in order to keep this to our roughly 30 minutes, I apologize for overrunning by a couple of minutes. Voice evacuation, we believe to be essential in high-rise environment. It's necessary to get people moving as quickly as possible in the orderly fashion that we want. Perhaps using one staircase rather than another staircase. It's important to be efficient. We believe we have the flexibility to do the projects in a different way, so we can adjust easily to the investor strategy for the project. And our system architecture, with the combination of small and larger nodes, I think is very well suited to that. And you know, on that basis, also actually using this shared and switched amplifier arrangement is efficient in terms of cost and cabling, and really it's the right way to go when you're looking at a lot of smaller landlord zones stacked up over many levels. So yeah, that's mainly really the things that I've been trying to get across to you in the last half an hour. I hope I've done a reasonable job. So I'm going to ask, we have reached the end of our allotted time, but you know, if you guys have any questions, this would be an excellent time to ask.